stop or should I?
No. We'll take care of
Fine.
it.
Okay, great. Okay, so the Newtonian force law is a very sorry is a was developed to understand, as I said, the motion of celestial bodies, understand the orbits of planets, and it was very successful at doing that. But in fact, the Newtonian theory, I think we should think about it also in a broader sense, is a quintessential example of what a successful physical theory should look like. And that's why, we still teach this theory even 350 years after it was discovered. And one of its virtues is that even though this theory was built to understand how the Earth moves around the sun or how planets move around the sun, in fact, it does a lot more than that. Often in physics, we have a situation where you build a theory that works in one regime, but it doesn't work in a different regime. In a different regime, you need a different theory. But Newtonian gravity is really very accurate over a large range of states. So even today, if you wanted to describe even today the motion of rockets that go off the Earth and that come back to the Earth also nowadays, that is very well described, at least the gravitational part of that motion is still very accurately described by the Newtonian theory. Similarly, if I take some pen here and I throw it up and I want to calculate, how high it goes, then that is also very accurately described by the Newtonian theory. Or alternately, I said the theory was developed to understand the attraction between the sun and the earth. But in fact, you could look at the earth and the moon, and that is also very accurately described by the same theory. So it's really a very successful theory. It's the kind of theory you really want to give as an example of a successful physical theory that has stood the test of time over a long period of time. Okay. However, this is not, the Newtonian theory does not represent our modern understanding of gravity. And the place where the Newtonian theory began to break down was discovered about 125 years ago, when people started to realize that there was something slightly unusual about the Newtonian theory. And what's slightly unusual, you can think of by thinking of the following thought experiment. So imagine, we have a giant, friendly giant. This giant will show up again and again in the talk, who comes and who pushes the sun a little bit. Okay, so the giant moves the sun away from where the sun was originally. More realistically, we could think of a supernova explosion that happens on the other side of the sun from where we are, and you have some emissions from the supernova that come and they displace the sun. So you could now ask, given that this has happened, when does the earth know that the sun has moved? Okay, now if this were to really happen, we might be more worried about our survival than to calculate this, but this is still a good thought experiment to ask about, which is how long does it take for the earth to know that the sun has moved? Now, if you take the Newtonian theory very seriously, then you would say that, look, the distance between the earth and the sun has changed, and therefore, the earth knows instantly that the sun has moved. And so the answer to this question in the Newtonian theory would be the earth knows immediately that the sun has moved. However, we realized, as I said, about 125 years ago, that this was not quite consistent with other principles of physics that we were discovering, and in particular, the idea that information cannot travel faster than the speed of light. Okay? In 1900 to 1905, we discovered the special theory of relativity through the work of Lorentz and Poincaré and Einstein. And one of the key principles of that was that, you cannot transmit information faster than the speed of light. And therefore, the Newtonian theory, which, as I said, is a very successful theory, has a problem in that it's not a local theory. It posits action at a distance, and action at a distance is not consistent with relativity. And so for this reason, we started to realize that we had to change the theory of gravity. And together with understanding, trying to make the Newtonian theory consistent with special relativity and also with other principles, one of them is important one is called the principle of equivalence. We developed a different theory of gravity that is still the correct theory for classical physics today. So the different theory of gravity that we today use to describe, gravity is called the theory of general relativity. And the theory of general relativity, some of you have probably studied it, some of you in this talk, is actually quantitatively, it's very similar to the Newtonian theory. It has to be quantitatively similar to the Newtonian theory because we know the Newtonian theory is so accurate. So whatever the corrections to the Newtonian theory are, must be small corrections. However, if you think of the ontology of the theory, the objects that it refers to, that is radically different from the Newtonian theory. So in the Newtonian theory, we had the same setup, the Earth and the Sun, the Earth and the Sun. And we said that, look, the Earth and the Sun get attracted to each other with a force. In the general theory of relativity, we do not talk of forces. Rather, we say that one shouldn't only speak of the Sun and the Earth. Rather, we should think of both the Sun and the Earth as being embedded in a dynamical space-time, and the space-time itself is dynamical, and the space-time responds to the gravitational effect of the Sun and also the Earth, but largely the Sun because the Sun is so much more massive. And as a result of this gravitational effect of the Sun, the space-time gets warped or gets curved in a specific way that we can calculate. And the reason the Earth goes in an orbit around the Sun is not that the Earth feels a force, but rather these orbits are the natural trajectories, the so-called geodesics, but in this warped space-time that is slightly different from the flat space-time that we are used to thinking about. So you can see that the language one uses to describe the same physical phenomena, which is that the Earth is going around the Sun, is very different. But the virtue of this language is that everything is interacting locally with everything else. Okay? So the Sun is warping the space-time near it, and the Earth is responding to whatever the space-time is doing near where the Earth is. So the Sun and the Earth don't talk to each other directly. There's a mediator, and the mediator is the space-time. Good. So, and of course, there are equations that go along with this. It's not just these words. And the equations that go along with this that were first understood by Hilbert and by Einstein are roughly that matter tells space-time how to curve. And that's this first equation. On the right-hand side, this piece, this T mu nu piece, the equations are not important for what I'm saying, just the picture is. The T mu nu piece represents the effect of matter. And on the left-hand side, we have something called the Einstein tensor, and that encapsulates the space-time curvature. And the second part of general relativity is that space-time tells matter how to move. And that is given by this equation. And this, this covariant derivative captures some effect of space-time. And this differential equation tells you how matter moves. Okay? So you have this interplay between matter and space-time. And as you can see, the language and the equations look very different from the Newtonian theory. But of course, it requires very accurate observations to distinguish between these two theories. Now, we can use this theory of general relativity to go back to the question that I started this talk with. And you could ask, when does the Earth know that the Sun has moved if our friendly giant comes and moves the Sun? And the answer is that in the theory of general relativity, that if the Sun is moved, then the movement of the Sun, causes ripples in this fabric of space-time. And these ripples in the fabric of space-time, one can actually calculate how fast they propagate. And in fact, they propagate exactly at the speed of light. And so these ripples in the fabric of space-time, they propagate at the speed of light. And after a time of 8 minutes, they reach the Earth. And then the Earth, therefore, knows after 8 minutes that the Sun had moved. Okay? So this is consistent, of course, with special relativity. But you see that to make it consistent, we had to introduce all this additional baggage. But in the end, it gives us an answer that we like, which is that information does not travel faster than the speed of light. Okay? Okay, good. Are there any questions about what I said so far? Just to be, maybe what I said so far was pretty simple and elementary for many of you. But just to make sure that we are all on the same page, if there are any questions, I'm happy to take them now. Otherwise, I'll go on and talk about other aspects of gravity. Okay.
I guess you can move on.
Fine. So I'll assume that what I said so far was clear. By the way, if one of you could please also monitor the chat in case there are questions there, that will be really nice. So I'll go on there. So in any case, as I said, this theory of general relativity was understood now about maybe 110 years ago. And then, people started understanding the theory. And very soon after the theory was discovered, the German mathematician Karl Schwarzschild discovered some interesting solutions to the theory. And this solution is called the Schwarzschild solution. And once again, the details of this solution are not important. The solution is just some exact solution to the equations of motion that I showed you previously, which represents a space-time that's very different from the kind of space-time we're used to. Is there a question? Someone had a question?
Say it. You can for a mommy. It is.
Dr. Yashwanand, will you please mute your mic?
Sorry, is there a question? Someone saying something? No. Okay.
I think it's an accident.
Okay, fine. Yeah. So as I said, very soon after these general relativity was discovered, the German mathematician Karl Schwarzschild found these exact solutions to the theory, which go by the name of the Schwarzschild solution, and I've written the Schwarzschild solution here. But the exact details of the solution are not important. What I want you to think about in this talk now is the picture of this Schwarzschild solution. And the picture of this Schwarzschild solution is as follows. Okay? So if you're if you're far away near infinity in this solution, then the space-time looks a lot like the flat space-time like it is around us. However, in the solution, this is the space-time which is plotted in some coordinates, and in the solution there is some region which corresponds to which is at a radius, which is proportional to the mass and has some constants that are not important, and this region is called the horizon. And what this horizon does is it demarcates two regions of space-time. And the interior of the horizon, everything inside the horizon, is called a black hole. And what is special about this black hole, this black region which is inside this horizon, is that the black hole has the property that once you enter the black hole, it is not possible to exit the black hole. However, and this is an important point, there isn't, if you have a big enough black hole, the horizon, this region, this interface that I've marked as the interface between black and red, is not locally distinguished. So it isn't that there is something dramatic that happens at the horizon that that you cross the horizon, but rather it's like an invisible Lakshman Rekha. So you can think of it as an invisible Lakshman Rekha. So once you cross it, there's no going back. But it's you don't know while you're crossing it that you crossed the horizon. Okay. But once you've crossed it, then you're inside and there's no way for you to exit it. And I'll explain a little bit more later why this happens. Okay? This solution that I described, the Schwarzschild solution, also has another special region, which is called the black hole singularity, which is the region at r equal to 0 in the coordinates that I described. But in fact, in this talk, I won't have much to say about the singularity, and I'm largely going to talk about physics near the horizon. Okay, good. So, when the solution was first discovered by Schwarzschild, and in fact, for much later, as late as if some of you open the Feynman lectures on gravitation, you will find the solution was misunderstood in many ways. And also, it wasn't necessarily thought that this was a real solution. People thought that this was a solution which was the mathematical solution, but who knows if such things actually exist, and maybe they don't describe anything in our real world. However, we now understand that these solutions called black holes, in fact, they exist wherever we look around us in the cosmos. And a few years ago, for instance, the Nobel Prize in Physics was given for understanding that at the center of our own galaxy, our own home, the Milky Way, there's a supermassive black hole called Sagittarius A star. And the way it was discovered was by looking at the orbits of stars around this black hole. And this is much more massive than the sun. It's 4 million times as massive as the sun. And because we are not near the center of the galaxy, it's about 26,000 light years away. Now, this is not the only, we know of many, many black holes, and we've studied black holes now in many different ways, including in the past 10 years or so, also through gravitational waves. So we now know that these solutions are not just mathematical artifacts, but in fact, they really describe the world around us. Okay, good. However, the dynamics and the astrophysics that goes into these black holes is very fascinating, and that's something that many physicists study. But the kinds of things that theorists like me like to talk about are what I sometimes call vanilla black holes. Okay. So in the black hole that I just described, the Sagittarius A star, the reason we know about the black hole's existence is because there are stars around the black hole and we can look at the stars around the black hole. But the presence of these stars, of course, creates its own complicated dynamics. And what I want to describe is something much simpler. So what I want you to think of is just one solitary star that lives in splendid isolation in the universe, or not even a star, just a blob of dust that lives, in solitary, splendid isolation in the whole universe. I mean, what that means is really that as physicists, we always like to study isolated subsystems. So you take the system and you just think of the system. And then, this system at some point starts collapsing. It starts collapsing under its own gravitational weight. And this dashed line is the horizon. And at some point, the system collapses so much, this dust is so massive, it collapses, that it is itself confined. It becomes smaller than its own Schwarzschild radius. And when that happens, no force in the universe can stop it from collapsing further. And it keeps collapsing till it basically becomes singular and infinitely dense. Okay. So this is the kind of process that I want you to think about. And in fact, I'll say in a few minutes how this process is extended once you start thinking of quantum mechanics. However, I first want to point out that, this is a cartoon which shows snapshots in time. So this is how the dust blob was initially, and then it became smaller than the Schwarzschild radius, and then it became, even smaller. But of course, we don't want to draw these snapshots in time. And so it's convenient to represent the same process that I showed you on what is called a space-time diagram that, again, some of you must have seen in your studies of special relativity. And what is a space-time diagram is, the usual kind of graph that you draw, except that on the y-axis, we think of time. Okay? So this is, in fact, the same process that I showed you previously. Here was this blob of dust on the surface of the star. It was big at some point, and it started collapsing. This purple region is the horizon. And you can see at some point, the star becomes smaller than its own Schwarzschild radius. That's this point. And then it keeps collapsing till it becomes a singularity. And the horizon is sitting here. So this solution was first, is often credited to Oppenheimer and Schneider. But in fact, a Bengali physicist, B. Dutt, about whom actually very little is known, I think, biographically, wrote down many of the equations that are relevant for describing this kind of a collapse a few years before Oppenheimer and Schneider. And in fact, also P.C. Vaidya helped to find a much simpler solution that represents the same process. And the fact that these singularities are formed and so on, the work of A.K. Rai Chaudhary contributed a lot to that. So Indian physicists have really contributed a lot to understanding this process of the formation of a black hole, okay, mathematically. So in any case, this is the same diagram, and I want you to keep these space-time diagrams in mind, where, as I said, time runs on the y-axis and space runs on the x-axis. Now, there's a further refinement I want you to make. I'm going to show you a third picture of the same vanilla black hole that I showed you previously. And this picture is what's called a Penrose diagram. So this is a slight refinement of the previous picture I showed you, where, remember, I said time runs on the y-axis and space on the x-axis. That is still true here. However, I have rescaled my spatial coordinates. So as you know, you can always rescale your coordinates rather than plotting on a straightforward graph. You can use a log plot, or you can use some other coordinates to plot. So here I've rescaled my coordinates, and the speciality of these kinds of diagrams, space-time diagrams, which are called Penrose diagrams due to the British physicist Roger Penrose, are that these diagrams have the property that light rays are always 45-degree lines. Okay, so this is the same picture that I showed you. Here's the star, and it's collapsing. Although in this picture, because I've rescaled space and time, it's not easy to see it's becoming smaller, but in fact it is. And it goes to this singularity, and the singularity is this point here. And this purple line is the same horizon that I showed you previously. This figure also helps explain a few more features which are important. Remember, I said to you a few minutes earlier that the horizon had the property that, when you crossed it, you couldn't see anything special. but on the other hand, there was no way to escape it. This figure explains why that is the case. And the reason that is the case is that the horizon, which is this purple dashed line, is a light ray. It is the trajectory of a light ray. You can see it's a 45-degree line. Now, one thing that's special about a light ray is that once a light ray crosses you, you can never catch up with it. So if I take a torch and I shine it and the light ray overtakes me, I will never, in the life of the universe, ever be able to catch up with that light ray. It's gone forever. So because the horizon is a light ray or represents the trajectory of a light ray, that's why once you cross the horizon, there's no way to go back. Also notice that if you look at this part of the horizon, which is at late times after the black hole has collapsed, there is no matter or anything at the horizon. This part of the horizon where my mouse is currently pointing is just empty space. So there's nothing very special about this region. It's just that there is a trajectory. It represents the trajectory of a light ray. And therefore, obviously, once you enter this, you cannot exit. And the diagram, in fact, shows you that any motion in the time-like direction, any motion in the y-axis, must bring you to this singularity, which is given here by this curved wavy line. Okay? Okay, so this is the third picture that explains the black hole collapse process that I showed you, and you should keep this picture in mind for what I'm about to say. Okay, good. So now our friendly giant is back. So I said, we want to think about vanilla black holes. But now, we want to do a little bit more. We already understood what we had to about vanilla black holes. So we call in our friendly giant. And we ask the giant to say, well, now we formed a black hole. Now we want to do some experiments with it. So the giant says, fine. And the giant takes the Earth and throws the Earth into the black hole. So you can then ask how the black hole responds if you throw in additional matter into the black hole after the black hole has been formed. Good. So now, of course, remember I told you that the horizon of the black hole was proportional to its mass. So you expect that when this happens, the horizon will grow, the black hole will grow a bit. And it's useful, once again, to think of this process in the Penrose diagram that I showed you previously. Here's a picture of the process in the Penrose diagram. Of course, we don't have giants in the Penrose diagram. And this is the same black hole that I showed you. And then this is the horizon. And then here's this orange line represents the trajectory of the additional matter, the Earth or whatever we threw in. And this falls in after the black hole has formed, which was here. And it goes in and it ends at the singularity. When this happens, the horizon, of course, grows as we expect it to do. But in fact, about 50 years ago, physicists, by studying this kind of a process, found that there were some rather precise equations that describe how the black hole responds when you poke it or you probe it in this way. And what people found was the following. They found that when you take some stuff and you throw some additional mass dm in the black hole, so say the black hole had mass m, and you add to it this additional mass dm, then the black hole changes, but the change of the mass is related to the change of the area of the horizon with a constant that's called the surface gravity, kappa over 8 pi, and plus additional work terms. And work terms have to do with the fact that the black hole could be charged. And so there might be, if you have some additional charge in, you might have to do some work to push the charge in. Or the black hole might have angular momentum, and if you might have angular velocity, and if you throw something in, you might change that angular velocity. That gives you the usual work terms that you get in physical objects. But in addition, there was this term that tells you that the change in the mass is related to the change in the area. And also people found that the area of the black hole could never be decreased. You might have thought that the right rule for black holes was that the mass of the black hole could never be decreased. But in fact, the correct rule is that the mass of the black hole can sometimes be decreased through a process called the Penrose process. However, the area always continues to increase. Now, this is very reminiscent of something that you study in undergraduate thermodynamics, which is that if you take some system and you change its energy, then the rate of change of, the change in the energy is related to the change in the entropy with a proportionality constant called the temperature. And then there are additional work terms that you study. One of them, for instance, is minus PdV. That term doesn't have an analog for the black hole, which doesn't have a well-defined volume. But there are the same work terms that you would have, which have to do with the electric potential and the charge and the angular momentum and the angular velocity. But also, for an isolated system, the entropy always increases, which looks a lot like the fact that the area always increases. Now, when this was first discovered, you might have thought that this was a case of just two systems obeying the same equations, but this was just a formal analogy. And this is the kind of thing that in fact happens a lot in physics. I'm sure many of you have read the Feynman lectures. And if you read the Feynman lectures, I think Feynman has an entire chapter which is titled "The Same Equations Have the Same Solutions." And in that chapter, he'll point out, for instance, that if you solve the mass on the spring, a mass on a spring, you can also solve the circuit of an inductor and a capacitor because they obey the same equations. So you don't need to do the work again because you already did the work once for a mass on a spring. However, and this happens all the time in physics. You often solve an equation in one setup and it appears in another setup. However, this does not mean that a mass on a spring is an inductor and a capacitor. It just means that those two systems have the same equations. They're just described by the same equations, but they're distinct physically. So one might have thought that these laws of black holes were similar to those of thermodynamics in that, they were the same equations, but in fact, they were physically somehow distinct. However, and that's this picture that I have here, that you have black holes and they obey the same laws of thermodynamics. But you might have thought that that's just a mathematical coincidence, as often happens in physics. However, Hawking found, again now about 50 years ago, that this wasn't quite correct. In fact, Hawking found that when you add quantum mechanics to the mix, then black holes are not really black. Rather, what happens is that quantum effects lead to the pair creation of particles near the black hole horizon. That's something that's happening in space all about us, where you have pair creation of particles. And the creation of particles at the horizon, what's special about the horizon is that if you have pair creation happening here, then one particle can kind of fall out and the particle that's behind the horizon will fall into the singularity. So if you have an observer who's somewhere here, just far away, it will seem to them that you just have a steady stream of particles coming from the horizon. And in fact, Hawking was able to calculate the spectrum of this radiation, and he showed that it corresponded to black body radiation at a specific temperature. And what is important here is that this taught us that the analogy between black holes and thermodynamics was not just a case of the same equations having the same solutions, but rather black holes really are thermodynamic objects, just like this cup of tea that I have here. Okay, so the picture when you add Hawking radiation to the mix, this is of course an exaggerated cartoon, is that you still have this region far away that looks like ordinary space. But at the horizon is not really black. Rather, there's some radiation that's coming from the horizon that in this case I've depicted as some ring of light, which is meant to indicate, this is a cartoon I emphasize, that you have stuff which is escaping from the horizon. And, the black hole is like a luminous object. It emits radiation, and it emits radiation with a particular black body spectrum with a temperature that one can compute. Okay. So as I said, Hawking was in fact able to compute the temperature of the black hole, and he found that the temperature was given with a factor of h bar. This shows you it's a quantum effect times the speed of light cubed times 8 pi times the Boltzmann constant, the Newton's constant, but 1 over the mass of the black hole. The only thing here that depends on the black hole, and this I emphasize, is the mass. So you have a black hole of a certain mass, provided it's spherically symmetric, it always emits black body radiation at this temperature. And you can convert this to SI units, and you will find that a black hole with the mass of the sun emits at a temperature of 6 into 10 to the minus 8 Kelvin. And this tells you that black holes really are thermodynamic objects. Okay, so now I've said some things about black holes and how the picture of black holes that we have is modified by quantum effects. Are there any questions about what I said so far before I go on to the next part of what I want to say?
Did you say something about kappa being surface gravity? What did you say?
Yeah, that was kappa. That's different from this K. Okay?
Yeah.
This is in fact, this is in fact the surface gravity. So up to some factors, up to some numerical factors, the term that appears here is the surface gravity. Surface gravity is 1 over m. One way you can think of it is that you can think of it as m over r squared, and r is proportional to m. That's why you find the surface gravity is 1 over m. So the temperature really is the surface gravity by 2 pi.
Okay, sir.
Sir, there is a question in the chats.
Yeah. I can't see the chat. Can you please reach out? Sorry.
Oh, okay. The pair that you referred
yeah.
to
Yeah.
is that a particle-antiparticle pair. That is, if
Yeah.
an electron is there on one side of the
Yeah.
horizon, then
Yeah.
will there be a positron on the other
Yeah.
side?
Yeah. It's a particle-antiparticle pair, but it's not asymmetric necessarily between matter and antimatter. So you could have an electron on one side and a positron on the other side, or a positron on one side and an electron on the other side. Okay. So gravity doesn't care about this. So you're right that it is a particle-antiparticle pair. But by the way, in the case of photons, it's one photon on one side and another photon on the other side. Okay. So they just have different polarizations. So some particles are their own antiparticles. So when you think of particle-antiparticle pairs, you shouldn't only think of electrons and positrons. You can think of photons and photons. So photons and photons are also particle-antiparticle pairs, or gravitons and gravitons. In fact, if you take a black hole, which is rather massive, most of its emission, if you look at the temperature, you will see, the temperature is low, right? So you see most of the emission happens only in particles that are, so that mc squared is smaller than this temperature itself, than the energy scale set by this temperature. And you will easily see that most of the emission from black holes, in fact, occurs in photons and gravitons, which are the massless particles, and not in stuff like electrons and positrons.
Sir, I had a question.
Yeah.
When a massive particle pair is created near the horizon, and the other particle, the one particle escapes and the other falls in, so does that increase the mass of the black hole?
No, it decreases the mass. It has to decrease the mass, and that has to do with it has to do with I'm not sure how to explain it in a very simple way, but one way you see it has to decrease the mass, and in fact that's what I'm about to say next, is that if you're an observer who's just far away, then you see that energy has to be conserved, right? So if there was stuff that was falling out, the stuff that's coming out, then it must be the case that the black hole energy itself is decreasing. And the way to understand that is that the notion of what is locally positive energy is not the same as what is positive energy for an observer who is far away. So this particle that's being created locally, you can think of it as having positive energy. However, for an observer who's far away, it really has negative energy. Okay? And so that's the reason that this particle that's falling in behind the horizon. That's the reason that you have this creation of pairs, but the mass of the black hole decreases. And you see, it has to be the case, because if there is radiation and energy is conserved, and energy must be conserved, then it must be the case that what remains behind has to lose mass. And in fact, that's going to be the next part of what I say. Yeah, I think there's another question. Is there any other question, or that's it?
Hello.
Yeah.
Ring that you spoke about in that you drew in your cartoon, is that the same as what we see in the Event Horizon telescope pictures, or is that a different one?
No.
This would be too weak for that, right?
The Event Horizon telescope doesn't actually see the horizon. Okay, so it's actually a bit of a misnomer. What the Event Horizon telescope sees is some region that's about thrice the size of the horizon. Okay? You can't really see the horizon. And this effect that I'm talking about is a quantum mechanical effect. And if you look at the temperature, you will see that for an astrophysical black hole, this radiation would be at 6 into 10 to the minus 8 Kelvin, which is much weaker than the cosmic microwave background. Okay, so it's important that to think about these effects, as I'll emphasize again. You should think of a black hole that really lives in isolation, that doesn't have the cosmic microwave background or something. Or else you should think of black holes that are not astrophysical black holes, black holes like maybe which have the mass of the Earth. And then you would find that this temperature would be appreciable. Okay? So for astrophysical black holes, Hawking radiation is completely negligible and certainly has not been seen by any telescope. And in any case, the Event Horizon telescope doesn't probe quite the horizon. Okay.
Sir, just to clarify your previous answer, so for an observer that is very far away, the black hole's mass is decreasing, but locally it is increasing. Is that what you said?
No. Locally, you can't define quite the mass of the black hole. So locally, what you can see is that you can talk about a particle. Okay? So there's some local notion that you can talk about. There's some, and with respect to that local notion, you never have negative energy. But to define the mass of the black hole, you really have to go out and take a global perspective. And if you do that, you'll see the mass of the black hole is always decreasing.
Thanks.
That's a good question, actually. And it has to do with the subtlety and how you define energy. Okay? So energy, you have to define the good definition of energy is in fact at infinity. That lets you define the energy, and that's always conserved. But locally, people might have particle detectors that you might think of as being positive energy, which might not correspond to positive energy at infinity. Okay. Thank you for the questions. That helps a lot. So in fact, I'm going to take off on the questions that were just asked. I didn't plant them, I promise you. As people were asking, what happens if the black hole radiates? And you see, remember that the total energy in the black hole is just mc squared. That's a famous formula we all know. And, the energy is lost through the radiation that is emerging from the black hole, as I just described. And in fact, this radiation is very accurately, the rate of energy loss is pretty accurately described by the Stephen-Boltzmann law. There are some additional factors that are called gray body factors of the black hole. But in fact, the energy is lost through radiation, and the rate of change of energy is just the area of the black hole times temperature to the power 4 times a constant, which, as I said, is related to the Stephen-Boltzmann constant and some gray body factors. But the important factors are the area and temperature to the power 4. Now, remember, I told you the temperature was proportional to 1 over the mass. The area is, of course, just 4 pi r squared, where r is the radius of the horizon, and the horizon radius is proportional to the mass. And so if you put those factors in, you will find a 1 by m to the 4th and an m squared. And therefore, the rate of change of the mass is minus 1 over m squared with some constant that I have presented for you here in SI units, which is 4 into 10 to the 15 into kg cubed by second. Now, what this tells you, if you take it seriously, is that if you continue to let this process happen, and it's important for this that the black hole really doesn't have stuff falling in like the cosmic microwave background or anything like that, then after a long time, and how long? After 10 to the minus 16 in SI units into m cubed, the black hole completely evaporates. Okay. In terms of numbers, as I said, you shouldn't think of this process seriously for solar mass astrophysical black holes, because there, the life of the black hole is 10 to the 67 years. And as you know, the age of the universe is only about 10 to the 13 years. And therefore, solar mass black holes are effectively eternal. On the other hand, there is nothing theoretically that prevents the existence of black holes that are much smaller. And so if you think of sometimes people ask me about the Bermuda Triangle when I give these talks. And if there was really a Bermuda Triangle and a black hole in the Bermuda Triangle, and this black hole were to swallow up a big plane that flew over it, that plane would have a mass of 400 tons. And so it would be just the right kind of physical setup we could do to see black hole evaporation, because it would evaporate quickly and in a time of about 5 seconds that you would get if you put in 400 tons into this formula here. But the main point is that, you can think, at least in terms of thought experiments, of black holes that form and that completely evaporate due to this quantum mechanical process of Hawking radiation. So, in fact, this brings me to what is called the information paradox. And before I explain the information paradox, let me just explain the picture that I've set forward. In the first part of this talk, the very first part, I talked about the formation of a black hole. And this formation of a black hole could be from some blob of dust or a star that had stopped shining. And this led to the formation of a black hole. And after a black hole forms, I said, there would be quantum effects. And quantum effects would cause the black hole to radiate. And the radiation of this black hole, if we let it go along long enough, will eventually just lead to the emission. And as I explained, the emission largely of photons and gravitons, also other particles, but exponentially suppressed if you think of the Boltzmann factor, to photons and gravitons, and according to a black body spectrum that just depended on the mass of the initial star. Okay. So this is the life of a dead star, as I have set forward for you so far in this talk. So Hawking, now about 50 years ago, used this to argue for a paradox that occurred in the presence of gravity. Okay. And Hawking's paradox was the following. Imagine that you have two stars. There's star 1, which forms a black hole, and that black hole radiates, and this process that I just described happens. But you have star 2. Now, star 2 has the same mass as star 1, but in fact, it's slightly different in that maybe it has a little more carbon, or it has, some more helium. It has slightly different composition. It has the same total mass. It also forms a black hole, and this black hole also evaporates into radiation. But in what I was describing to you, I told you that the radiation was black body radiation that just depended on the temperature of the black hole, and the temperature of the black hole was inversely proportional to the mass. So it doesn't care about the difference between star 1 and star 2, whether star 2 had more helium or less helium or more carbon. It's just the same radiation. And that suggests that you could take these two distinct stars and run through this process and get the same radiation at the end. So you start from two different initial conditions and end up at the same final condition. This is actually a big problem. It's a big problem if you think about it for a little while, because in all of physics, from whatever we have learned, from childhood, a very fundamental property of physics is that time evolution is always reversible. So in physics, when we are given problems in our textbooks, we are often told, you take a ball, you set it off with some velocity, how far does it go and where does it land? But in fact, you can often ask the other question, which is, you're given a ball, it lands here with some velocity, where was it launched from, with what speed? And you can solve for that as well. And if you think about the Schrodinger equation also has the property that you can solve it forward in time, but you can, given a state, you can also understand where it came from by solving the Schrodinger equation backward in time. So in all of physics, we always have reversible time evolution. And the idea that time evolution might not be reversible in the presence of black holes is a very serious threat to our basic understanding of physics. And this tension between some effects that we get from quantum mechanics and from gravity and a very basic property of physics is called the information paradox. And it's been an important paradox that has helped us understand many interesting things about quantum gravity. Okay, so I now want to explain, so I hope the formulation of the paradox is clear. I now want to explain some of what the paradox has taught us about, both statistically and also about some unusual features of quantum gravity. Okay, good. So let me first make a simple point. And that simple point, is there a question?
Yes, sir.
Yeah, go on.
The point you were saying about the reversibility, it only
Yes.
applies when there is time reversal symmetry in the system, right?
No. The fact that reversibility, all systems are reversible. Time reversal symmetry is a question of whether, things look exactly the same physical laws govern what happens as you go back in time. And often, in fact, in realistic physical systems, apart from changing time, reversing time, you also have to change charge, and you also have to change charge into a reflection. But the fact that one initial state goes to one final state is completely independent of that. That's just a very basic feature of quantum mechanics. It comes from the fact that you have, psi of t is e to the minus iht times psi of 0 in quantum mechanics, and e to the minus iht is a unitary operator. So time evolution operators are unitary, and therefore you can also invert them. And that's also true in classical physics. If you look at evolution, that evolution is a differential equation, second order differential equation in time, which you can solve forward and backward. So whether it looks exactly the same, even if there is some difference in solving it forward and backward in time, you still can solve it forward and backward in time. So one state leads to one final state and one state in the past. So reversibility is really very fundamental. Doesn't rely on any symmetry like time reversal symmetry.
Excuse me, sir.
Yeah.
Sir, I have heard in situations in particle physics, T violation occurs, right? When in cases of some weak interactions.
Yeah.
I have heard that.
Yeah, I just explained that it doesn't have to do with time reversal symmetry. The fact of reversibility has nothing to do with whether, you see, there are two different questions you could ask. You could ask, when I run physics back in time, is it exactly the same physical laws that are obeying the physics backward in time? Or do I also have to change something else? Do I also have to change particles to antiparticles? So do the physical laws look slightly different when I run physics back in time? That's one question you could ask. The second question you could ask is, and that's the question I'm talking about here, which is, given one initial state, can you determine the past and can you determine the future? And is the future unique and is the past unique? That does not have to do with the answer to the first question. The thing you're talking about is whether there is symmetry. Here, there's no issue of symmetry. I'm just saying that given one initial state, you get exactly one final state. And given one final state, you have exactly one initial state. Okay? It doesn't have to do with symmetry. It's just that it's a one-to-one map. You know, let me give you another example. F of x is equal to 2x is a one-to-one map. Okay. The inverse of that is that f of x is half x. It's not the same as the forward function, but it's one-to-one. Okay. So the fact that you have a one-to-one bijective map between initial and final conditions is different from saying it's the same map. Okay. Do you understand that?
Yes,
So what you are talking about is whether the map is identical forward and backward in time. And indeed, as you said, that has to do with a question of symmetry. But the fact that it's bijective is much more central. And so in quantum mechanics, the important part is that the map is unitary. Okay, does that help?
Yes, sir. Yeah, got it, sir.
Okay, great. Are there any other questions? Okay, excellent. Good. So let's go on. So, as I said, the information paradox has been very useful because it has taught us some interesting things about physics. And what has it taught us? So one of the things that, the information paradox has taught us is also to think carefully about the limitations of Hawking's computation. And that's the first point that I want to make for you. Okay? So here's the zeroth order solution to the information paradox. It's the fact that, look at, this is a cartoon once again. And this is my cartoon picture of the black hole. And here I've plotted some photons. You can think of these as photons of different wavelengths. And this is a computer-generated image. This is not representing realistic black hole emission or anything like that. It's just a computer-generated image of different dots placed with a random distribution on the screen. Okay. And indeed, if you look at the distribution of any one dot, the probability that the blue dot was here or the red dot was here, that's just some distribution that's confined to some region that I put on my computer. So it's just some random distribution and it does not by itself contain any information. However, if you look at the joint probability distribution, so I emphasize, if you look at the joint probability distribution of two dots, you will start seeing a pattern. In this case, this is the pattern. Look at a purple dot here. And if you look at the purple dot and you trace it through this black disk, you will find a yellow dot exactly on the opposite side. If you look at the red dot and you trace it through this black disk, you will find on the other side a blue dot. The point here is that the joint probability distribution of two objects or more objects might contain more information than just the marginal probability distribution of a single object. This is the statement that sometimes, if you just look at one random variable, you have many random variables, you might not have much information. But once you start looking at correlations of two or more of these random variables, then you might find that there is a lot of non-trivial information in that. And what is the cartoon in the screen in front of you gives you an example of how the joint probability distribution might have more information than these marginal probability distributions. So Hawking's calculation that I just showed you was really about the marginal probability distribution of the emission of a single particle. And I told you that obeyed the Planck distribution. Fine. But that is not precise enough to tell you about the joint probability distribution or the correlations of one particle and another particle. And in fact, if you keep track of these correlations, I think I don't have a slide, but maybe I can annotate here. You can check that the correlations between, you can have e to the minus, let me write here. Sorry. Let me go back. Yeah, let me just annotate here. So you can have e to the minus s sized correlations between in s point correlators. Okay. So here what I've shown you on the cartoon here is what's called a 2-point correlation. It's a correlation between two random variables. But you can have correlations of size e to the minus s between in s point correlators. So that would be a correlation that would only be apparent once you took into account S points, where S is the entropy of the black hole. So remember, I told you that the black hole had a temperature. In fact, associated with that, it also has an entropy. And that entropy is, in fact, 1/4 of the area of the black hole. And it's very large for a black hole. For the sun, I think it's 10 to the 70 or something like that. And so, the correlations can be exponentially small in the entropy. And they might be evident not when you look at 2-point correlators, as in this cartoon, but when you look at S-point correlators. And the zeroth order answer to Hawking's information paradox is that Hawking's calculation was simply not precise enough to keep track of all of these correlations. This is something that, in fact, we see all around us. Notice that if I take this cup of tea and I swirl it, you could ask me, I was telling you guys that physics is reversible. I was making such a big deal about it. Now you could say, well, given the initial condition of the tea here, which is it's at rest, can you compute what was the velocity with which you swirled it? And the answer practically is, of course, no. And the reason it's no is that information has dissipated into a lot of other degrees of freedom. So it has gone away into many fine-grained degrees of freedom that have to do with the cup and me and the room and the chair and other things. And so it has dissipated everywhere. And only if I keep track of all of those degrees of freedom with great precision can I understand, what was the initial condition of the tea. Yeah? And so this kind of dissipation is something that we also see around us in ordinary statistical systems. And the zeroth order answer to Hawking's paradox is that Hawking did not keep track of these fine-grained degrees of freedom in the radiation. And therefore, Hawking's argument, just by looking at temperature, is not precise enough to lead to a paradox. However, this is not the totality of Hawking's argument. This is an important part of understanding the resolution to the information paradox, but it's not quite the totality because, in fact, Hawking had a second argument that was a little refinement of the argument I just gave you.
Sir, there is a question.
A question. Yeah, go on. Yeah.
It says, how is it true that the purple dots are opposite yellow and red is opposite blue if the image is completely random?
Yeah, good.
Okay.
Yeah, exactly. Good. So the image is not completely random, right? So the answer to the question is that the image is not completely random. But if you look at the position of any one dot, it is completely random. But of course, the image has more information than the position of any one dot. So if you look at the probability distribution of any one dot, that probability distribution is the same as just a random probability distribution of placing a dot in this disk. But if you look at the joint probability distribution of two dots, you will find that that has more information than the probability distribution of any one dot. So this is something that can often happen where you look at the probability distribution of one variable and it just looks like a random probability distribution that doesn't have any information. But when you look at the joint probability distribution, it shows you more patterns than the probability distribution of only one variable. Okay, so that's exactly the point that I was trying to make. Okay, good. So however, as I said, this answer that I gave you here is the same answer that explains why physics around us is dissipated, even though I made a big deal of saying Schrodinger's equation is unitary, evolution in classical mechanics is unitary. Some of your friends could ask you, but we see dissipation all around us. How is that consistent? And the answer is what I just gave you. That in fact, unless you keep track of very fine-grained degrees of freedom, if you keep track of coarse-grained degrees of freedom, it will look like evolution is dissipative. And that is the zeroth order answer to Hawking's paradox. However, Hawking had a refinement. And the refinement was, I said that you needed very fine-grained information, but Hawking said, and in fact, many people sometimes don't realize that Hawking made this point. Hawking said that, well, but let's think about it a little bit more. Now, you're saying that this radiation has some very fine-grained degrees of freedom that keep track of information. However, this radiation is really emerging from the black hole horizon or from the vicinity of the horizon. But the horizon, as I showed you earlier, does not have any trace of the infalling matter. It looks like the matter has all fallen in. And therefore, it looks like the radiation is emerging from some region that is space-like separated to where the matter is. Now, this is related to the thing I told you in the beginning of this talk. Remember, I asked you about, if the sun moves, how long will it take for the Earth to move? And we said we didn't like that to happen instantaneously. And the resolution was that things which are separated by spatial distances shouldn't be able to communicate. And so that's what we are seeing here. Hawking said that, look, when you move, when you have this radiation coming, it's separated from where the matter is. So how can there be any information about the matter in the radiation? You're telling me you have these small correlations, but that's not possible. Because look, these correlations are forming from here, and this Hawking radiation is coming from this region here. And therefore, it looks like the horizon is free of information. So now I want to explain something. This is the last part of what I want to say, that we have learned in the past few years. That is, in fact, an unusual feature of quantum gravity, and and that helps to understand why it is that this paradox can also be sidestepped. So this has to do with a very unusual feature of gravity that we call the principle of holography of information. Many of you have probably heard of holography in gravity. This is a slightly different statement. It's also a slightly weaker statement. It's slightly more broadly applicable. And the statement is that in a theory of quantum gravity, whenever you have a geometrical situation of this kind, this is a snapshot at one instant of time, where you have a region R and which is surrounded by its complement. If you think about this, this always happens when the region R is bounded. So complement just means you look at this complementary set. Then all observables in the region R can also be represented by observables in the complement. Okay? This is a very unusual statement. It doesn't happen in any other theory. It's telling you that all information about what's there in the blue region is also available in the purple region, maybe in a scrambled way, but some observer doing complicated observations in the purple region can in fact determine what's happening in the blue region. Okay, so this is called the principle of holography of information that we have understood in the past few years, that helps to understand why this second point raised by Hawking is also not really creating a paradox. And what this principle implies, and I'll explain in a few minutes why you should believe that something like this principle holds. What it implies is that the region outside the black hole always retains a copy of the information that falls into the black hole. And so it is not true that the horizon is information free. Rather, the horizon is rich in information when you look at it carefully enough. And the region outside the horizon, in fact, keeps a complete track of what fell into the black hole. And that is why information is not lost. So we have to modify our idea that you had this matter which fell in and it carried all the information away with it. In fact, if you think more carefully about effects of quantum gravity, it turns out that observations near the horizon can also keep track of what was the details of the matter that fell in. Now, in the last 5 minutes, I'm going to explain to you quickly why you should believe that a property like this should be true in a theory of quantum gravity. I won't have time to give you details, but I'm going to try and give you a basic undergraduate physics explanation for why something like this should be true. Okay, so I'm now going to give you, remember the principle I'm trying to prove. I'm trying to tell you that if you have information here or some degrees of freedom here, I should be able to make observations around it and determine, what happens in this region. Okay, so I'm going to give you a basic undergraduate physics explanation that's based on the Heisenberg uncertainty principle and the gravitational Gauss law. Those are the only two physical principles I'm going to invoke, and I'm going to try and give you an argument. It's not a proof, what I'm about to give you. Of course, I can't give you a full proof, but I'll give you an argument for why what I said is true. So first, let me remind you of the Heisenberg uncertainty principle. I'm going to phrase it in a slightly unusual way. The way the uncertainty principle is usually phrased is that if you think of a wave function that's localized in position, it can't be localized in momentum space. But let me phrase it another way. Because momentum goes together with energy, let me point out that a state which has definite energy necessarily has a wave function that extends out to infinity. Okay? So if you want a wave function that's strictly zero outside some bounded region, then you cannot get it if you also want to think of an energy eigenstate. So energy eigenstates are always delocalized, and that's a version of the uncertainty principle, but stated in terms of energy rather than in terms of position. Good. So this is something that's familiar, but of course, this doesn't stop us from creating states which are localized in quantum mechanics. Well, how do we create a state which is localized? We think, this is localized here. It's not where you are, so I can have this T, but you can't. And of course, the reason for that is that we think of wave functions which have some energy, but we can also think of superpositions of wave functions. So if we take an energy eigenstate and we superpose it with another energy eigenstate and a third energy eigenstate, and we take an infinite number of such superpositions with the right phases, then we can arrange for destructive interference outside a bounded region and constructive interference in that region, which gives rise to a wave function that's of this kind, which is strictly zero outside that region. Now, what's different about gravity? This is just true in quantum mechanics. All of us know this. In quantum mechanics, if you think of how to construct such wave functions, it's very easy for you to construct wave functions that are just zero outside some bounded region. They might not be energy eigenstates, but who cares? They're superpositions of energy eigenstates. Well, what's different about gravity is the Gauss law. And what does the Gauss law tell you? The Gauss law tells you that the energy of some object can be measured from infinity. This is actually a very interesting law because it also holds in the general theory of relativity. In fact, those of you who might have studied GR or might have taken advanced courses and studied GR will know that the only good definition of energy in gravity is by taking the gravitational flux at infinity and integrating it. And that gives you what's called the ADM Hamiltonian, which in fact measures for you the energy inside a region. Now, you might ask me, well, in the beginning, I told you that, information is not propagated instantly. Now I'm telling you that if you have the Earth here, you can make some observations around the Earth and determine the mass of the Earth. So you could have said, what if the mass of the Earth suddenly changes by half? How could the observer here know that the mass of the Earth had suddenly changed by half? Does any one of you want to guess an answer to that question, by the way? How is this consistent with what I told you, that general relativity is local? Now I'm telling you that you can get the energy here by doing some integral of the gravitational flux here. Okay, does any one of you want to guess an answer? No guesses? No.
I mean,
Okay.
we are seeing from infinity, right? So the mass will vanish. It will be still inside the region.
Well, okay. Let's not be at infinity. Let's be a little away. Let's ask. Well, okay. So let me. Someone could say, let's say we are not at infinity. Say we are at a finite radius. Let's say we are where we are, and someone could say, we have a set of planets that surround the sun, and what if the mass of the sun suddenly reduced? So remember, I said in the beginning a giant came and moved the sun, but what if the mass of the sun went down by half? You could have said, if I did a Gaussian integral around the orbit of the Earth, I could determine that instantly, and that seems like a violation. However, the question is wrong, actually. The reason the question is wrong is because the mass of the sun cannot suddenly change by a factor of 2. All of you have studied that energy in gravity is conserved not just globally, but locally. Okay? So the mass of the sun cannot change by a factor of 2. The premise of the question is just completely wrong. The only way the mass of the sun can change is for this sun or this object to break up and some of its mass to exit this Gaussian surface, as I'm showing here with my mouse. When that happens, of course, it's not a surprise that the gravitational field here changes. So that is why the Gauss law is consistent with locality. It's because energy momentum is locally conserved. And that is why, the energy here can be measured by some degrees of freedom here. And that is not inconsistent with locality. So that's something you should keep in mind. Okay. The fact that the energy can be measured from far away is not inconsistent with locality because energy is conserved. And the only way the energy got in here is it came from outside. And that the fact that it came from outside leaves behind a kind of memory. And it's that memory that you measure when you measure the Gauss law and measure the flux of the gravitational field. Okay. Okay, but this is just about the classical Gauss law. How is this related to the effect I told you in quantum gravity? Okay. Remember, by the way, in classical gravity, the Gauss law is true, but it is not true that I can determine everything that's happening on the Earth from far away. In fact, you have studied in the Newtonian theory and also in general relativity something called Birkhoff's theorem that tells you if you take a spherically symmetric shell of mass, the gravitational field outside here only depends on the mass. So if you reorganize the mass, while keeping spherical symmetry, there's no way an observer here can determine what's happening in the classical theory of gravity. So what happens when you add quantum mechanics to the mix? Well, let's go back to the picture, as I said in quantum mechanics, let's go back to the picture of an energy eigenstate which was delocalized. Now, when you think of a theory of quantum gravity, the constraints of quantum gravity, the Gauss law tells you that you cannot have something like just an energy eigenstate of some particle or some system without also having a gravitational field whose flux at infinity gives you the energy. So the correct kinds of states to think of in quantum gravity, these are sometimes called solutions of the Wheeler-DeWitt equation, are states of this kind, which have a certain energy, but they coexist with a gravitational field. They have to coexist with a gravitational field, and the gravitational field all the way out at infinity. By infinity, I just mean you go very far away, you integrate the flux, and that integral tells you what the energy is. So you always have a particle together with its gravitational field. This is sometimes called a gravitational tail. So every excitation must be dressed with a gravitational tail. Good. Now, how does this modify the picture that I showed you? Well, let's go back to the picture I showed you where I said you superpose a number of different waves so as to have constructive interference in a region and destructive interference outside it. Well, in the presence of gravity, you're out of luck. Because remember, every excitation is coming together with a gravitational tail. And this gravitational tail goes all the way out to infinity. And it is this effect that prevents destructive interference outside a bounded region and constructive interference inside a bounded region. And I emphasize it's not just the energy, but it's correlation functions of the energy and other observables that carry complete information about the state. So what I gave you is a very quick hand-waving argument for why information is localized differently in quantum gravity. And it has to do with just two simple physical principles, the uncertainty principle and the Gauss law. And in fact, if you put both of them together and think carefully enough, the results are rather profound and they lead you to this very unusual property of gravity, which is called the principle of holography of information. Okay? So here's a picture to summarize what I said. In a theory without gravity, you can think of this kind of a cartoon where things outside this region look like the vacuum and you have some excitation inside the room. So you can have something inside the room. If you wait for some time, then eventually information from here will leak outside. But on an instant of time, you can set up a configuration of this kind where the observer here thinks everything is the vacuum. What is more, you can change the configuration. In fact, this is what we mean by information, in such a way that things still look exactly the same for the observer outside. In a theory of gravity, first, you can't do this, even in the classical theory, because the moment you have an excitation here, the observer outside knows there's something inside because they can measure the Gauss law. But in the quantum theory, I said there's an even stronger statement, which is the moment you try to even change the form of the excitation here, the observer outside can make some measurements and can determine that something changed. In the case of the black hole, if you think of this as being the matter inside the black hole, it changes some quantum aspects of the wave function at the horizon, and it's that leads to information emerging in the Hawking radiation. Okay? So due to these effects, the region outside the horizon is not free of information, which is contrary to what Hawking thought, because of course Hawking didn't know about these unusual properties of gravity, which were learned about much more recently. Okay, so this brings me, in fact, to the end of the physics points I want to emphasize. I want to, point out the two key points you should keep in mind, which we understand from the information paradox. And the two key points are just because, simple observables, first of all, look thermal, doesn't mean that the microscopic state has lost information. This is the cartoon that I showed you, which tells you might need to look at many observables at the same time to see that the state has information about the initial matter. But then Hawking said, well, even that's not possible because it looks like the horizon is information free. But in fact, when we think a little more carefully, we find that quantum gravity localizes information very differently from classical gravity and non-gravitational theories. And as a result of that, the region outside the horizon, when you look at quantum fluctuations of gravity and other fields, is not free of information, but in fact is mapped in a one-to-one way to the matter that fell in. And that is how information enters the Hawking radiation that is produced by the formation of a black hole. Okay, so that's all I wanted to say, but let me end on a slightly philosophical note. One thing, we started this talk by talking about the Earth and the Sun and the Newtonian force law. And I said, well, the Newtonian force law is very accurate, it's very good, but it has this property of action at a distance. And so it's not a local force law. And so we didn't like that. And so we invented, we came up with this theory of general relativity, which is a local theory where we have this fabric of space-time where everything affects each other locally. But now when we think more carefully about quantum effects and quantum gravity effects, we find that, in fact, things are a little more subtle. And in gravity, you cannot quite localize information the way you do in non-gravitational theories. And that leads us to this rather interesting effect, which is in the end a statement about quantum gravity independent of black holes. It's just a phenomena of quantum gravity, which is this holography of information, which is that if you have an excitation in this bounded region, there are some observables far away that always keep track of what was in the bounded region. So it's kind of a perspective, we haven't got back to action at distance or anything like that, but it's kind of a progression of our perspectives on gravity and space-time and locality that's interesting to think of. Okay, so thank you for your attention. I'm sorry for going a little over time, and I'll stop here and take more questions. Thank you.
Sir, I had a question.
Yeah, go on.
So in the principle holography of information, when a thing falls inside a black hole, its information is encoded in the complement of the black hole.
Yes.
So the complement region of the black hole is the entire universe.
Yes.
So can the information be present anywhere in the universe, or is it a growing sphere with the speed of light around the black hole?
No, it's not. I think that the statement is you take the picture you take a Cauchy slice. So you take a spatial slice. In fact, maybe I should share. I should have stopped sharing. 1 second. Yeah. So let's go back to this picture. Yeah. So let's take this blue region. This blue slice is actually an instant of time. Okay. So what it's telling you on this blue slice is that information about the matter is available on this blue slice. But there is a constraint. It's the same quantum mechanical observable. In quantum mechanics, you have something called a no cloning theorem. So it can't be that there are two observables that are distinct that carry the same information. However, the observable that measures some property of the matter on this part of the blue slice has another representation. It's a redundancy in description, which is that you measure some observables here, and they also carry the same information as the observables in this part. So if you measure quantum fluctuations of the metric and other matter fields in this region outside the horizon, which is this part of the blue slice, they carry complete information about the inside. And of course, that's complete information about the state. So it's not a question of a growing sphere. It is that you take any instant of time and you look at what's outside, and sufficiently accurate measurements outside keep track of what's inside. Now, if you think further and think of the Hawking radiation that's produced here, then this Hawking radiation, of course, is sensitive to the details of the metric fluctuations and other stuff at the horizon. And therefore, it's not surprising that it also keeps track of the information that's inside in the infalling matter. You shouldn't think of that information as being localized deep inside, but rather it is also present here. And so a process here is sensitive to what's happening inside.
Sir, is it like entanglement?
No, it is not like entanglement. Actually, that's a good question. Thank you for asking it. In entanglement, it is not the case that processes here are sensitive to what's happening inside. Let me explain why. So imagine you had a blue dot and a red dot here. So sometimes entanglement is misexplained by saying that the blue dot and red dot have information about each other. But in fact, that's not the case. Because if I take the blue dot and I act with, so let's say I have two qubits which are entangled. If I take the qubit that I have with me and you have another qubit in Mohali, and I act with a unitary operator on my qubit, then you will not have any information about the unitary operator that acted on my qubit. So you will measure your qubit, but your measurement is completely insensitive to what I did to my qubit. So you're not really measuring my qubit. What you're measuring is some correlation. So maybe we initially prepared the qubit so that my measurement would be the same as yours. But after I have acted with the unitary, it's no longer the case. So you make your measurement and your measurement is completely unaffected by my unitary. Here, a much stronger statement is being made. Here, the statement that's being made is there is no unitary you can act with here in this region that does not affect something outside. So in ordinary non-gravitational theories, there are local unitaries that are confined to this region that are completely insensitive to the observer outside. In gravity, there is no local unitary operator that is confined to this region that does not affect some observable outside. So it has to do with the lack of existence of local unitary operators, which is not true in entanglement.
Thank you, sir.
Okay, and the other questions? I see a question in the chat. Yeah, a question is, one of the slides ends up with a singularity, but in Hawking's. Yeah, so, this point, the question is that I stated earlier, matter ends up with a singularity, but now I'm also saying a copy is at the horizon. So, I think this picture explains things once more. The singularity is actually far in the future, when you think of the causal nature of the space-time. If you think of a spatial slice through the space-time, it actually doesn't have the singularity, which is in the future. And what happens is, what's being said here is not that the matter is at the horizon. The matter is not at the horizon. The matter is where it is. But information about the matter is available at the horizon. Whenever one way to think, just think again of the classical Gauss law. The sun is where it is. How do we know the mass of the sun is 2 into 10 to the 30 kg? We haven't been to the sun. But the gravitational field of the sun carries information about the mass of the sun. So there is an observable which corresponds to the mass of the sun, but you could go to the sun and measure it. That's not a good idea, of course. But alternately, we can measure the gravitational field of the sun where we are, and by doing that, we get the same information. So it's not that the matter of the sun is here, but rather that information about the matter is carried by the gravitational field. And in the quantum theory, I said that all information about the matter is carried in the gravitational field. In the classical theory, it's only the total energy that you know about. But in the quantum theory, you know about more. So it's not that the matter is created, but rather that the gravitational field and other fields here carry information about what's in the interior. I hope that answers the question. Are there any other questions?
Sir, may I?
Yeah, sure.
Sir, in one of your slides, you talked about gravitational tails, and excitations must be addressed with a gravitational tail. What
Yes.
do we mean by it? Like quantum mechanically?
Yeah, it means that if you want to think of a wave function of, say, a particle, say you have a field, and you want to think of an excitation of the field. The reason I said excitation is just that we think of all particles as excitations of a field. When you think of an excitation of a field in quantum gravity, you cannot think of a configuration in which only the field is excited and the gravitational field is completely in the vacuum. When you think of an excitation, it has to be that the field is excited and at least the constrained components of the gravitational field are also excited so that the Gauss law is preserved. That's what a gravitational tail means. So you cannot think of a configuration in which there's some matter or some energy so that this field is not in the vacuum, but the gravitational field looks exactly like it does in the vacuum. That's what it means. So the metric also has to have its wave function changed if you change the wave function of other particles. Does that explain it?
Yes, sir.
So in the follow-up question, I didn't understand how does tail prevent from constructive and destructive interference? Like
what?
The fields are gravitational field. How is the field a gravitational field preventing from constructive and destructive interference?
Yeah, it's this picture here. So I did give you a proof. I was just pointing out that earlier, you remember how did we do constructive interference? What we did was we took wave functions of some particle and then we just superposed them, right? And when you can superpose, that's how, if you think of how you make a wave function localized in quantum mechanics, if you think of it in energy eigenstates, you will see you need an infinite number of energy eigenstates with carefully engineered phases. And you can arrange for that wave function to have destructive interference. But now imagine this wave function comes together with another degree of freedom, which is different for these different energy eigenstates. Now it's not so easy to make them interfere destructively, right? Because remember, there's another degree of freedom that's being carried together with them. And that prevents the destructive interference of just these parts of the wave function. That is why it isn't possible to have just these parts of the wave function interfere destructively, because you have a second degree of freedom that extends all the way out to infinity. Now, what I'm giving you right now is not a proof. You could have said, well, maybe I can do something cleverly. And therefore, what I'm giving you right now is not a proof, but I'm trying to explain what the physics behind it, what the physical intuition is. And the physical intuition is you don't just have the wave function of the matter field or the excitation, but you also, it's correlated with the gravitational field. And it's for this reason that you can't just superpose the left-hand side and get constructive interference outside in a bounded region and destructive interference outside, because you also have the gravitational field sitting with it.
So are you saying even if I do constructive and destructive interference of quantum field, I will still have non-zero gravitational field outside?
You'll also, yeah, so you will not be able to arrange for a configuration which is of this kind, of the kind on top, where you have some quantum field excitation inside a bounded region, and things here look outside exactly like the vacuum. The flat region is meant to say everything here is exactly like the vacuum, but something in the middle is changed. So you cannot do this because of what I said. There are other big time gravities of this kind. Yeah, there's a question here which is causality is not violated because of local conservation of energy, and any change, that's right. Region R must be related to some change in the complementary region R. But that's correct, exactly. You could have asked, why doesn't this picture violate causality? I said that if you change something here, you also have to change the tail. And you could have said, well, that looks like a violation of causality because I could change something here and I would have to change the tail. But in fact, in gravity, all changes have to come from infinity. They all have to come from outside. Otherwise, the dynamics here is completely autonomous. It's only when you send something from outside that can change it. And that's why it's not this cartoon that I'm showing here, which is you change something in the middle, you also have to change something outside, is not inconsistent with causality because of what I said. And, I use the word memory. That's actually not a bad word because it's, the reason something is changed here is because this change here went from outside in the past. So it's like a memory, but memory is also used in a slightly different context in gravitational physics, in terms of in terms of the soft limits of the gravitational field and these BMS symmetries. So if some of you have studied advanced DR and know about memory in that context, I'm not referring to that memory. I'm just referring to memory in a more mundane sense, which is that this change of the gravitational field had to have come in from outside. And it's that change that, leaves some imprint that you can keep track of.
So the memory is is it the gravitational tail, the memory?
Yeah, it is partly the gravitational tail, but it's also other fields that remain. So this is a slightly subtle point, but indeed part of it is the fact that there's a gravitational tail that remains. But you have to be a little bit more careful. So in fact, in the end, this cartoon here is slightly misleading because it's not just the gravitational tail, but correlators of gravitational fields with themselves and with other observables that keep track of everything that happened inside.
I guess that's it, sir.
Okay, great. So let me stop. Okay, so thank you. Maybe it's, time for your dinner.
Thank you very much, sir.
Okay.
We hope we can host you in ISER itself physically one of these days.
Sure, yeah. I'd love to.
Thank you very much, sir.
Thank you so much, sir.
Okay, thank you guys and see you.